All right, let's get started here. We're going to go through some review about our derivatives of our trig functions like we did yesterday. But I wanted to prove something because we ran out of time last time. Why is the derivative of sine of x cosine, negative cosine of x? Okay. Now remember the idea of a derivative is slope, change, instantaneous rate of change. That's really what it is. What is that change at that very instant? Okay, so let's draw a sine graph. A sine graph goes 0, 1, 0, negative 1, 0. You guys remember the pattern from pre-calc? That's for any sine graph. And you go a little backwards, it goes back to negative 1 and back to 0. Just lay that out. Remember this cycle continues back.
Positive.
Hmm?
Is it negative cos or positive?
This is the derivative of sine becomes negative cosine. But what I'm drawing right now is just a regular sine graph.
Okay.
So looking at the unit circle, just to make sure you guys are cool with this, the sine is your y value, right? Y is our sine graph. Okay, y is our sine. So at 0, the y value is 0. At pi over 2, the y value is now 1. 0 to pi over 2, to pi, to 3 pi over 2, to 2 pi. So if sine is your y value on your unit circle, at pi over 2, our y value is now positive 1. Positive 1. At pi, our y value is now 0. See the 0 here? At 3 pi over 2, our y value is now negative 1. Negative 1. And at 2 pi, our y value is back to 0. Okay? So 0 decimal to 1. 1 decimal back to 0. 0 decimal to negative 1. And negative 1 decimal to 0. And that's how we end up with this graph here. So I want to ask you though, okay, as we look at this graph here, what is the slope of this graph of sine? So let's draw another graph here. And I want you to just point out, when is the graph equal to 0? Okay, correction, major correction. Yeah, derivative of sine is cosine. Dang it.
Wait, so Mr. Ko?
The derivative of cosine is negative sine. Oh my gosh, sorry. I'm still on my roof. Okay, give me a second. Okay, made that dumb mistake. All right, the derivative of sine is cosine. Okay, so I want you to look at this graph here and please tell me, or in your head, when is the slope 0? When is the slope a horizontal line that's flat? And it happens at pi over 2, happens at 3 pi over 2. Over here on the left, happens at negative pi over 2. So what happens, we're gonna graph those values right now. Just to make this easier for us, the derivative is 0 on these points, which is pi over 2, 3 pi over 2, negative pi over 2. Those are easy, okay? Got it? The next thing I want you guys to ask, hey, is the slope positive or negative here? So like a roller coaster, you guys been on a roller coaster before COVID? So the roller coaster starts off slow and then goes really fast and then slows down again. Okay? It goes slow, fast, slow. And that's what the tangent lines look like. It's a little dip, a major dip, and then a little dip again, back to 0. So it's looking over here, please look over here now. It's a little negative, really negative, right? Really negative, and then it has to come back to 0. So if you remember in pre-calc, when you graph roots, you gotta go from root to root. You can't go, woo, I would have to have another root. So an illustration of that is that all the slopes are negative. Okay, let's look a little bit to the left here. So let's look over here. We went from 0, positive slope, super positive, to slightly positive. Little positive, big positive, back to little positive. Little positive, big positive, back to little positive. Okay. Little slope, big slope, and then back to little slope, and then back to 0. Let's finish the right side to 2 pi. That's little growth to big growth. Little growth to big growth. Please look at this graph now here. If you remember 1, 0, negative 1, 0, 1, this is a cosine graph. The slope of a sine graph is really just the cosine graph. The cosine graph predicts all the changes for the sine graph. Okay, you guys hanging in there? So now we said, what is the derivative of cosine? What is the slope of cosine? Okay, let's draw in the line here. So this we said was a cosine graph. So it turns out the derivative of sine, the slope, the derivative is cosine. Let's take a look at the derivative of cosine. So like what we did before, go ahead and tell me when the graph is 0, when the tangent line has a 0 slope. 0 slope, 0, 0, 0. Okay. So it's 0, 0, 0. Everyone kind of okay with that? Those are my zeros. Okay. So from this section here, is the slope positive or negative? Am I increasing or decreasing? Decreasing. And the tangent lines look like little, large, little. So the graph goes a little bit negative, very negative, back to 0. On the right side, this is all positive right here. It's all positive, right? So it's a little growth, big growth, back to little growth, back to 0. And this is a negative sine graph. So the derivative of cosine graphs equal to negative sine graphs. Okay. So visually, it should make sense also, which is kind of cool. All right. Okay, so the derivative of sine is cosine, not like what I mentioned before, negative cosine. It is sine becomes cosine. But cosine, why is it negative? Because take a look here. The cosine, right when you take the first step off, it is a loss. That's why it's all negative here. It's the sine graph, but it's a negative version of it. Okay. All right. Let me pause here. So today we're going to do exponents, exponentials actually, and logs. Okay, so we're just going through the gambit of everything you learned from Algebra 1 to now. We're going to take the derivative of it. It's like cooking everything in your kitchen. Okay, here we go. What is the derivative of e to the x? Answer is e to the x. Okay, but I need to say something. I could go and give you the rule and give you all of them, but kids mess up on this. Because if I give you d dx e to the 2x, does this rule look like that? It's not a perfect fit, right? And what happens is we have to see this as this type of problem, d dx of e parentheses 2x. Okay, so we have an onion now, like we mentioned before. What's the outer onion, the e or the 2x? Outer onion is the e. The derivative of e is e. Copy the inside. You must protect the inside. Once you're done with that, take the derivative of the inside. Sometimes I say to don't look here, look up here. Okay? At your onion. So this becomes 2e to the 2x. Give you guys another one while we're at it. D over dx. E to the x squared.
Wait, Mr. Cole.
Yes?
So why'd you multiply it by 2, the e to the 2x?
So this is actually a chain rule problem.
Oh.
Okay, chain rule. So the outside layer is the e, the inside layer is the 2x. It's kind of like sine of 2x. The derivative of sine on the outside is cosine. We leave the inside alone. Then we multiply by the derivative of the inside. Oh, sorry,
Okay.
that's just 2. Better?
Right. Mm-hmm.
Cool. Let me just make me cry. Man up. I'm just kidding. E to the x squared, 2x. Ooh, too fast, Mr. Go. But the point about derivatives is that you can do them pretty quickly. Okay. Is everyone okay how I got the 2x here? So that's the derivative of the x squared. Now, please be okay with this. The derivative of e is always itself. It's like its evil twin. And then the evil chrysalis comes out afterwards.
So you keep e and then you
Yes.
do the derivative of the
Right.
exponent.
Look, it's like, but they're like total twins except for one thing. As I mentioned before, everything is chain rule. E to the x is actually chain rule. The derivative of e to the x is e to the x. Now, what's the derivative of x, right? We copy the x down. What's the derivative of x? Isn't that just 1? Don't write the 1. And this leads me back to what we talked about before. Well, what's the derivative of sine of x? This is actually chain rule. The derivative of sine becomes cosine. Leave the inside alone. What's the derivative of the inside? 1. So that's why we just write cosine of x. That's a fast way to get there, but we're actually always taking the derivative. Another way of looking at me taking the derivative of x, what's the derivative of x? Hey, don't they cancel out to become 1? That's like an algebra way of looking at it. Okay. All right, so now that we got the derivative of e to the x, let's do another one. What's the derivative of e to the u, right? Where u can be any function. So this is where the chain rule example comes out. This is d over d, oh, sorry, whoops. The derivative of e to the u is e to the u itself, protect the inside, times the derivative of what? The inside with respect to x. And this is literally chain rule. Leave the outside alone, and then we multiply by the derivative. Okay, so the cool thing about e, I mean, it's kind of awesome, right? Now, what if it wasn't e? Remember these exponential values are really just different powers? What's the derivative of a to the x? Where a is no longer 2.7 blah, blah, blah. E is just a number, 2.7, blah, blah, blah. So this rule is a to the x ln of a. Ooh. Example, d over dx of 3 to the x is 3 to the x ln of 3. That's just what it is. D over dx of 5x, that's just 5x ln of 5. So a is just a constant value. But here is something kind of interesting. Isn't e also a constant, just like pi? Right? We just write e because we don't want to write 2.7 blah, blah, blah. So let's do this. D over dx of e to the x following this rule is e to the x ln of e. Now, do you guys know what the ln of e is? Some of you guys might know it. Let me write it the long way. Log base e of e. That's what natural log is log base e. How many e's does it take you to get back to e? 1. That's why this is e to the x times 1, which is just e to the x. Back to our original definition, which is kind of cool, I think. Okay. So the derivative of e to the x is really e to the x ln of e. And then what happens is natural log of e becomes 1. So that's why it's just e to the x is e to the x. Now, what if I mix this up? Of course, it's going to always get a little dirtied. D over dx, let's say 3 to the x squared. Okay? So what do we take of the derivative of first? 3 or x squared. Outside the onion. If you need help, draw parentheses. Helpful. So the derivative of 3 is 3x squared. Don't be afraid to leave it alone. That is the outside derivative. Done. But you're not done with the derivative because we now have to take the derivative of the inside, which is 2x. That's your answer. You could simplify, make it look prettier, sure, but that's it.
So when a number or variable other than e is there, you have to put ln.
Right, because actually this is the original definition.
Okay.
Our e to the x is actually just a shortcut that we don't have to write this because this always becomes 1. So you can think of a to the x as a general for any number in the world. Well, e is a special number because e and natural log of e and natural log cancel each other out to become 1. Okay. All right. Now, let's give ourselves a weird one. Here's my example. Sine of e to the 3x. I'm going to take the derivative of this. Okay, what's your outside onion? And as we peel that onion, don't cry too much. But the derivative of the outside first. Derivative of sine is cosine. Leave the inside alone. It's okay. It's okay. Once I'm done with the outside layer, multiplied by what? Derivative of e to the 3x. That's just e to the 3x. Okay, we're done with the e now. Followed by the chain rule again times 3, because the derivative of 3x is just 3. Okay, I'm gonna give you guys one to try by yourself. I'm gonna give you guys 30 seconds to do it. D over dx of tangent of 3 to the x squared. Let's see if you guys can get this one. I'll give you guys 30 seconds. Don't be afraid. Don't need to simplify. Don't simplify. Do you see what I see? Let's see if I did this right. The derivative of tangent is secant squared. Leave the inside alone. The derivative of 3x squared is 3x squared. Leave the inside alone, right? Times ln of 3. Done. Last layer, the derivative of x squared is 2x. If you want to go into the matrix one more time, the derivative of x is 1 into that matrix. If you really want to.
Mr. Cole?
Yes.
So you used ln in this second example. So why didn't we use ln in the first one? With the...
Because this was E, and this was the number 3.
Oh.
Okay.
So with
If
E,
you
we
want
don't
to,
have to?
right, we don't have to because let's write it again. Let's do this derivative. I'll do it the long way. If I use this a to the x, okay, equation, I'm going to rewrite it. D over dx of e to the 3x is e to the 3x ln of, not 3, sorry, ln of e. What happens to ln of e?
It's 1.
1. That's why we don't write it,
Oh, yeah. All right.
which is kind of cool because it means the rule works. There's no special reason. We just get to cheat our way through it, shortcut it.
All right.
So it's really just a shortcut. It's like we write d over dx of x squared. It's just 2x. But really, you should be writing that because the derivative of x is 1. The long way of writing this is d over dx squared is the derivative of d over dx. Oops. It's going to be 2x d over dx of x, because that's the chain rule, right? It's the derivative of the outside parentheses, leave the inside alone, multiply by the derivative of the inside. Okay. All right. Let me pause here. Any questions? So now let's do the derivative of logs. Okay, so remember, logs are inverses of exponents. Exponents are inverses of logs. Okay, so here's the easiest one. The derivative of natural log of x is equal to 1 over x. It's really the derivative of ln of x is 1 over x. Then you take the derivative of x again, and that becomes 1, right? Chain rule. So this is totally chain rule again. Okay, the derivative of, so the idea is the derivative of any ln means you just put 1 over the inside. Let's look at an example of that. D over dx natural log of sine of x. Okay, so what natural log does is it says you are now on the bottom. Copy the inside. It's 1 over crap. The derivative of natural crap is 1 over crap. Okay, and we multiply that by the derivative of sine because of chain rule, cosine of x. Let's do this again. The derivative, natural log of, let's do x squared, becomes 1 over x squared, because that's what happens to the derivative of natural log. It always goes 1 over whatever is on the inside, multiplied by chain rule, which is 2x. If you want to go into the matrix again, by 1.
Can you simplify 1 over sine x times
You
cosine
can.
of x?
This could be cosine over sine, and that's cotangent.
So like on an IXL problem, we would have to simplify it to that.
Probably. Yeah. This one here would be 2x over x squared, which is 2 over x. Okay, let's do another one. Oh yeah, let me do. No, let's go into our next rule. Okay, let's do this. D over dx. Oh yeah, ln of u. So let me ask you, does this u and this x, they're not the same thing, right? So you still follow our rule. Take the derivative of the outside, which is 1 over u. That's not a problem. I just copy the u. Natural log, the derivative of natural log is 1 over crap. And then we say, what's the derivative of u? What's the derivative of u? And we can write this as 1 over u, u prime. So these are the same meaning, right? U prime is another way of saying take the derivative of u. And that's really what we did here.
And u equals anything, right?
Any function you want. And this is just a way of saying chain rule. The derivative of natural log is a fraction. And then don't forget to chain rule that sucker. Okay. Okay. And then the last one here is, oh yeah, there's a couple of things that we have to be careful of. Back here, just be aware that this is x is greater than 0. Okay? X is greater than 0. Because you can't take a natural log of a negative number, so it doesn't exist anyways. Let me remind you guys, you cannot take a natural log of a negative number. Why is that? Log base e of x, okay, equals to blank, okay? So can you say log base e of negative 2? E to what exponent gives you a negative number? E times E times E times E times E times E will never be negative. So you can never get a negative number out of this. Okay, remember, logs solve for exponents. This is an exponent. So E to what exponent will give you a negative? Never gonna happen. So that's why this is first greater than 0. Next thing is, can I plug in 0 here? Nope. So that's why it's greater than 0. There's one more rule here, just on the side. D over dx of natural log of absolute value of x. This is still equal to 1 over x, but x can't be 0 now. That's all. Okay. That one won't be used as much, but just FYI. Now, let's do one more log. This is just a regular log, not a common log, just a log with a random base. D over dx log base a of x. So what do we say happens when we take the derivative of log or natural log? It goes 1 over x. Okay? And now we have one more thing, ln of a. Take a look. How does this look like natural log of x equals to 1 over x? Don't they look really similar? But the natural log, you have to remember, goes on the denominator. Let's do a problem. D over dx log base 3 of, let's say, x squared. Okay, what happens to the derivative of log? It goes to the bottom squared. Since it is not a common, so it is not a natural log, we have to write ln of 3. Now I'm going to write this same exact log, except d over dx log base e of x squared. Okay. Now remember, log base e can be rewritten as natural log of, natural log x squared. Is everyone okay with this notation? Log base e is the same as natural log. So these are synonymous with each other, okay? So let's take the derivative of them together to see if they give us the same answer. 1 over x squared natural log e times chain rule, which is now 2x. And if you want to enter the matrix, you write 1 again, because the derivative of x is 1. On the bottom, 1 over x squared times the chain rule 2x. And what happens is natural log of e gives us x squared. It's the same problem. It just gives us a shortcut. If it's a log base e, we just call that natural log. The hard part is, will you remember this in 4 months? No, see, that's the hard part.
I don't think I'll remember this today.
Yeah. So the big thing is that when you're multiplying, when you're taking the derivative of exponentials, it's multiplying by ln. And if you're taking logs, it's dividing by ln. Okay. Let's see. Let's do one more example here. d over dx. We'll do log of 10 x squared plus 2x. Okay. Let's see what you guys can do with that. Okay. A couple things to make note. You cannot take the natural log of 10. So we are stuck here. Okay. That's just what it is. And then you cannot divide this out. Some kids will say, oops, and this is x plus 2. Nothing divides out. Take a look, nothing divides out. Okay.
You can't divide out the 2x?
No, you can't just do that. Okay, and let me show you why. Just as an example, if I write 102 divided by 100, 1002, you can't just divide it out the tens. No, just go the tens. Just go just the zeros top of that. Okay. All right. Any questions? Seem pretty okay? Okay, cool. So on our rule sheet, we mentioned some stuff like you can't, when you take the derivative of natural log or logs, they have to be greater than 0. So if I write here, where's my keyboard? ln of x. If you look at this graph here, see how the graph is all positive, right? It doesn't exist on the left side. So you can't tell me that the derivative exists here. That's why they wrote x is greater than 0. It doesn't even touch 0. So you can't tell me there's a slope when the graph doesn't even exist. Next one is natural log absolute value of x. Let's see if this will work. Parentheses around the argument. I don't know why. It didn't work. Let me try again. Oh, it won't keep it in the graph. Kind of weird. It says use a parentheses. Doesn't mean anything. Okay, let's do another one. It's just to do a log graph. Okay. You look at this log graph, same type of graph. So if I take the derivative of that, we can't be negative.